In this lecture, we're moving into our first main theorem, is the Carathéodory theorem. Before I go there, so recall last time we made this definition of an outer measure as defined on all subsets of X. As we see, the outer measure itself may not be a measure, it's defined on the entire power set of X. But what the Carathéodory theorem is going to tell us is that this outer measure, when restricted on a smaller sigma algebra, you will always get a measure. So this smaller sigma algebra consists of all the outer measurable sets respect to this outer measure, basically. All right, so let's first make the definition. If you took PMATH 450, this will be quite familiar to you. This is exactly how we constructed the Lebesgue measure. So let's let mu star to be an outer measure on X. We say a set is mu star measurable if it satisfies the following, basically saying if I have any E inside X, so here's E, and I can divide this E into two parts. One is coming from A, and the other is coming from a complement. Okay, so A can be some set over there. And a set is mu star measurable. This set A is called mu star measurable if this division will break the outer measure of E, as you would expect. The outer measure of E has to be equal to the outer measure of E intersect A, any part that's not in A. So this is the definition. And just want to remark one thing. Because outer measures satisfy the subadditivity, so you always know that the mu star of E is always going to be less than or equals to the right-hand side, because the union of the two things on the right will give you E back. Okay, so one direction is always the case. That's always true. So in order to show something that satisfies this equality, so you only need that the other direction. You only need to show the mu star of E is actually bigger than the right-hand side. So it only needs to satisfy this condition. And you may also notice if mu star of E is infinite, then the right-hand side by the subadditivity is, of course, has to be infinite. So you always have equality, infinite equals to infinity. So you only need to verify the second inequality if the mu star of E is finite, all right? So that's what the implicit assumption is right now. All right, so let's move on to the Carathéodory theorem. Here's the Carathéodory theorem. Suppose I have an outer measure on X, and recall that the outer measure is defined on the power set of X. Usually the power set is too big as a sigma algebra. So what we do is that let's only consider those mu star measurable sets, and let's give it a name, let's call it B. Then the Carathéodory theorem says, first of all, this B is in fact a sigma algebra. And second, if you just consider your mu star, you pretend that it's only defined on the sigma algebra B, then you actually get a complete measure, all right? So this is the theorem we're going to prove. So I will break the proof into two parts. So in the first part, let's show that B is actually just an algebra. Okay, we only show it's actually closed under finite union. We'll leave the sigma algebra part and the measure part to the next video. All right. To show that it's an algebra, well, we just need to show the three things. So first of all, the empty set is inside B. You can convince yourself why that's the case. Fairly simple. And the second, if you have A is inside B, then you can show that the A complement is also inside B. So here I use this notation A upper C to denote the complement. You may notice I prefer the X takes away A to denote the complement, but soon we'll have too many complements, so this is an easier notation for us. So just for simplicity. All right, why this is true? Well, you can also convince yourself. Basically, you're using the complement of the complement is A itself. So it's not too hard. I'll leave it as an exercise. So you only need to show it's closed under finite union here. We're only showing as an algebra in this video, so only closed under finite union. And the good thing about finite union is that if you can show it's closed under union of two sets, well, then you can use induction to add more and more, so it's always closed under finite union. So let's show that it's closed under union of two elements. So let's let A and B be some elements in B. Let's show that A union B is actually also in B. Okay, so here's what we want to show. Well, to show that's inside B, again, I just need to show the A union B satisfies the desired equality, or as we observed before, we only need to show the inequality. So here is what I need to show. I need to show that the outer measure of E, when you break it into two parts, the A union B part and the A union B complement part, then you get something smaller, okay? So here is what you want to show, okay? So here's want to show. All right, so let's start from the left-hand side, okay? Let's look at what this mu star E, how can I break it using A and B? Well, I will have to break it down, but I cannot use A union B directly. I don't know whether A union B is measurable yet, but I know A is mu star measurable. So let's break it using A first. Okay, so I know this is A intersect E intersect A, and I have a mu star of E intersect A complement. All right. Now you use the fact that A is mu star measurable to break it into these two parts. Well, how about B? You know, B is also mu star measurable, so you can break sets using B. Well, you have to somehow make A and B together. So how about I have two sets here. So how about I break each of them using B? So for example, the first one, I can further break it into the part that's actually in B, and then the part that's actually not in B. So I have A intersect B complements. They're the same. And I do the same for the second half. I consider that's actually inside B, but not in A. And the part that's actually not in B and not in A. So now I have equality. Basically, I break this mu star of E into these four parts. Let's draw a picture. So suppose my set E is here, and I have A and A complement, and the B is, you can use a different one. So here is B and B complement. Then essentially what you did is you break it into these four components. You have the A intersect B, which is the first one. You have the A intersect B complement, and you have the other three, basically. Okay. And if you look at these four, and let's remind ourselves what's our goal. Our goal is to show that the sum of these four is actually greater than equals to the sum of these two sets. Okay. So now let's take a closer look how these sets are related. So first of all, this A union B complement, well, that's not in A and not in B, so that's A complement intersect B complement. And that basically corresponds to the last part. Okay, so it's this part, okay, which equals to that. And they're basically the same. So let's write an equal sign here. So I have the second half of the desired inequality as my last term of these four terms. How about the first three? Well, let's see what's the first three. Well, the first three, I have A intersect B here, and then I have that's everything inside A but not in B, and the thing that's inside B but not in A. If I union these three parts up, well, what I get? Well, I get basically everything that's either in A or in B, so that's in the union. So because the union of these three sets is equal to this one, okay, so the union of these three equals to E intersect A union B, well, what I can have is that by the sigma subactivity of this outer measure mu star, the mu star of the E intersect A union B will have to be smaller than the sum of these three. That's the sigma subactivity, okay, or just subactivity of the mu star. So by subactivity, you have that the mu star of E intersect A union B is less than or equals to these three sums, okay? Sum of these three, okay? So now what do we have? We have overall this mu star of E, which is equals to the, first of all, I have a sum of three terms, sum of the first three. And then I have the second part, which I know is mu star of E intersect A union B complement, all right? But the first part by our inequality here, that's greater than or equals to the mu star of their union, which is E intersect A union B. And again, I have the second part, which is the mu star of E intersect A union B complement. So I have the mu star E greater than or equal to these two sums. And as we observed before, this is enough because the sigma subactivity tells me that this is greater than mu star of E, so I have equality here. All right, so this proves that the A union B is inside this set B, so B is an algebra.